Okay. Well, let's get going. I'm disorganized and it's all just mayhem. And I had some MATLAB simulations that I was supposed to show you, but now I'm not sure whether I can do it. So let's do the best that we can. Let's not waste any more time. And then if I need to record the video again, or I need to do a different video, but okay, let's just get going. That's right. If I was a few minutes later, you'd be all allowed to go home and get into bed. Okay. All right. Welcome to Wednesday's lecture. It's going to be a little bit ad hoc, but we're going to continue our investigation of the bifurcations. We're going to look at the transcritical bifurcation and the pitchfork bifurcation. And I would love to show you the lecture notes and show you where we are in the lecture notes, but I have no setup other than this camera, so you're going to have to bear with me for today's lecture. Okay, so let's remind ourselves what we were trying to do. Beginning with the Monday class, we were trying to solve this equation here, and we started looking at the most basic balance of the saddle node bifurcation, and in the saddle node bifurcation, you have a 1-2 balance. And then what we did was we said, let's look at the next simplest balance, not a 1-2 balance, but if this A1 term were equal to 0, then you would have to seek a balances with the remaining terms, and so you ended up balancing 2, 3, and 4, and we argued this was the only possibility as long as these coefficients were non-trivial, in particular if the B naught coefficient is non-trivial. Okay? So then balancing those three terms, we obtained this quadratic equation that we solved, and we ended up with solutions. The key thing to notice for these solutions, so this is giving you an approximation of the fixed points near the bifurcation point, right? The bifurcation point was assumed to be at 0, 0, and this is giving you an approximation for the two fixed points that exist when you're slightly away from the bifurcation point. Okay, so now notice that this quantity here, these will be just numbers depending on what goes into these coefficients. And this, in particular, this lambda here, you can assume it to be positive if these points are to exist. So this lambda, I'm just going to rewrite the delta is equal to b1 squared minus 4 b naught b2. Okay? And it should be greater than 0 for the fixed points to exist. And be real. We're always talking about real dynamics here. Okay? So provided this condition is true, then this will just give you some value, some number, and you'll have a fixed point on either side. And so the picture that we drew, if I draw this graph of these two approximations, where I have an x plus and x minus associated to this plus and minus, then these are just lines. They're lines of two different gradients given by the two plus or minuses. So for example, I have one line going through like this and another line going through like that. Okay, so this will be, let's say this is x plus. This will be a constant times mu. And then this is x minus. This is another constant times mu. Notice I've not shaded, and let me just plot the mu here and the x here. I've not shaded the lines here. I've left them solid because we haven't made a decision about stability. Okay, but we're gonna basically do a toy example of this. You're gonna do a canonical example of this transcritical bifurcation, and that will allow us to figure out what the stability is. And what we're going to find, in fact, is that there's an exchange of stability, so that before the bifurcation point at the origin, this is dashed, this is going to be unstable, this is going to be stable, and then as it passes through the bifurcation point, the stability will change. What was previously the stable fixed point then becomes unstable, and this is unstable, and it becomes stable. Let's look at an example. So this is in chapter 5, and it's pretty much just following the notes. So just with, obviously, with a little bit of elaboration. Okay, so the bifurcation we found, and someone had asked in the last lecture, what's the reason for the word transcritical? And I meant to think about that. The bifurcation we found is called transcritical. The transcritical bifurcation, and a transcritical bifurcation is one in which you go from two fixed points to two fixed points. And it's one in which the stability, though again we've not shown it, we're going to do it for the example, but it's an example where the stability changes. Like so. Oh, sorry. You know what? All right. Is that a bit better? Okay. Okay. So now you can see it's written the bifurcation we found is called a transcritical bifurcation. Two fixed points goes to two fixed points, and stability changes. So let's look at a canonical example of this. Canonical just means prototypical, a prototypical simple example of this transcritical bifurcation. Let's take f of x and mu to be equal to 1 plus mu times x minus x squared, like so. Okay. And, okay, so step 1, go find your fixed points. Step 2, find their stability, and that's it. So step 1, let's find our fixed points. So let's solve x equal to f of x. Okay, so you've got x is equal to x plus mu times x minus x squared. So x equal to 0, or what do we have? X is equal to mu, yeah? So you always have a fixed point at the origin, and you always have one at mu. So if mu is less than 0, then it's on the left. If mu is greater than 0, then it's on the right. Okay? Number 2. So how do you get the stability? To get the stability, you take the derivative, fx, then you substitute in the point. So fx is equal to, take the derivative of that, it's 1 plus mu minus 2x. And then you have to evaluate fx at 0 to check the first fixed point. You get a 1 plus mu. So if mu is less than 0, then this quantity is less than 1, and you're stable. If mu is greater than 0, then this quantity is greater than 1. So this tells you that if mu is less than 0, it's stable. Whereas if mu is greater than 0, it's unstable. Notice, by the way, that when mu, so whenever I do this, people point out, oh, actually, you haven't checked the other side of it, right? You haven't checked that when mu is equal to minus 2, actually this is equal to minus 1. Why haven't you done that? And the reason why I haven't done that is because right now we're just discussing the region around the origin. But I'll write a little note here. So note fx is actually less than minus 1 if mu is less than minus 2, but we are focused. Can you all see this? We're all focused on 0, 0. Okay? Because this section of the notes is about analyzing the behavior near 0, 0. That's a local thing. You're just looking at it locally. We're not that interested at the moment of looking at the global behavior of the function. So even though this function here changes stability as well when mu is equal to -2, we're mainly focused on the region near 0, 0. But it would have been perfectly fine if I said, go and do the full analysis, then you should go and find those other points where this quantity, the magnitude, exceeds 1, or greater than 1 and less than -1. Okay? So next you're going to go and take the derivative and substitute in the other point there. Let's do that over here. Fx at mu. Okay, so this is 1 plus mu minus 2 times mu. 1 plus mu minus 2 times mu, like this. That's 1 minus mu. Okay, so if mu is less than 0, that's greater than 1. So that's unstable. Okay, if mu is greater than 0, then fx is less than 1. So it's stable. Okay, and as well with the symmetry here, you will have an issue if mu is equal to 2, because then you're on the other side of the stability threshold. You're on less than -1, but again, it's not something that we'll worry about. Okay, so again, note that in fact, the fixed point goes unstable for mu greater than 2, greater than or equal to 2, I guess. But we focus near mu is equal to 0. Okay, hopefully you all understand that subtle point about local analysis versus global analysis. When you do this series expansion, you're just doing a local analysis. You're studying a zoomed in region near the origin. And so this classification that we have is valid near that zoomed in region. For these toy examples, we can solve everything. We can solve for the fixed points, we can solve for the stability kind of everywhere because they're super simple equations. But in this chapter, we're mainly looking at local analysis. So it's just a warning for you, because I know a lot of students will read the notes, and in the notes they wonder, well, why don't they mention in the notes these other points where it goes unstable or where the stability changes? And that's just simply because the notes are very compact, and it's just doing the local analysis. Okay? All right. So that essentially establishes the dash to solid picture, or the solid to dash picture that I showed you before. But let's plot this picture here, and then we'll see, let's plot the cobweb diagrams for this picture here so that we can see this process of stability changing and the movement of the fixed points. Now, if I was super brave, I would try to access MATLAB online. Those of you who did your MIGs with me yesterday know all about our trials with MATLAB online. And on MATLAB online, I've put in a folder for you. There's a folder there called Lecture number 8, and I have the scripts that I was planning on showing you with the cobweb diagrams. But just because I'm quite disorganized today, I don't want to fiddle around with more stuff that might kill my computer. So once I get that sorted for you, we'll show you on the Friday class these pictures about using the simulations, using MATLAB code to show you the cobweb diagrams. Today we're just going to do things just by plotting it by hand. There's an excellent question. So someone has asked, can we use our Taylor series approximation to give us information about regions away from mu is equal to 0 and x equal to 0? And it's a very deep question, in fact. And the point here is that, in theory, you might argue, actually, I can go infinitely far in my series, or I can go to 50 terms to 100 terms. And that might actually give me some information about the behavior away from these special points. Can I not just do that maybe with a computer, or just be just be much more diligent in my series approximation. And the issue that you have to worry about, and I say this is very interesting, you can spend a whole course talking about this. The issue you have to worry about is that when you write down this series approximation, you make a certain assumption on the ordering of the terms. You're making an assumption that each term is, in a sense, getting smaller and smaller, right? Now, this is essentially true for convergent series, right? But the problem is that this series may not be convergent everywhere. And what can happen then is that actually the terms will they might, for example, get smaller and smaller, then they might get bigger and bigger. And so you're trying to put in values of x and mu when you're not that sure about the convergence properties of that series. So the basic answer to your question is, yeah, you can begin to go to higher order. And if you really sit down and study it and spend a week really dissecting the particular series, you might be able to glean some information about the behavior away just from, this microscopic region around 0, 0, but it would depend on the particular function that you're given. Some functions, you might be able to do that. You might be able to walk away a little bit further from 0, 0 by going to more and more terms. Other functions, maybe it's a lot trickier, right? And that deals with the precise convergence properties of the function. As long as the function is smooth and well behaved, then you can always write this down around 0, 0, but all bets are off when you begin to walk further away. That's the basic idea. And you can think, for example, of the geometric series. So I'm allowed to basically take the geometric series around the origin. Anything past a magnitude of 1 away, then the series begins to diverge, and I have to question the legitimacy of my series approximation. But it's an extremely interesting area of mathematics, is to understand the progression of these series in different situations. Okay, now we want to return to our canonical example, 1 plus mu times x minus x squared, and we want to plot the two different pictures. Now, in your homework and in exam problems, sometimes you're asked to plot cobweb diagrams, and this, I think, is something I need to address. In a separate class to give you tips on how to do it in an organized fashion. And I think the problem is that when you, if you're given a question on a problem set or on an exam and it says, use cobweb diagrams to make some sort of conclusion, you're not sure which ones should I be drawing. The trick is essentially that you want to draw the cobweb diagrams in the different limits, in the different interesting limits of the problem. And in this case, there are only two interesting limits. There's basically mu less than 0 and mu greater than 0. In some problems, you may need to draw different values of mu to get an idea, and it's a bit of an art to figure out which values of mu should I draw. But this is something that you'll get more experience in as you do more problems. But for the moment, we're mainly interested in the two situations, mu less than 0. We know there's something exciting happening around mu is equal to 0. We're going to plot it firstly with mu less than 0 and then see what happens. There's our line y is equal to x, and obviously I'm just doing a sketch here. This is not an exact picture. I know that there's always going to be a fixed point around 0, and I know that when mu is less than 0, there's a fixed point on the negative side of this, okay? And basically when you draw this diagram, just make sure that the gradient here is fairly steep, and then it's shallow here because there's no intersection on the right. And it's not a very nice parabola, I know, but it just gets the picture across. So this is our left fixed point. I can't remember what this was called. Let's call it the x minus fixed point, and this is our x positive fixed point, which is equal to 0. Okay? And the key thing is to notice is, again, always look at the gradients of the function. This is a steep gradient here compared to the line y is equal to x. So you know that this here will be this will be unstable, right? So you know that the cobwebs will move away from that fixed point. On the other hand, this one here has a shallow gradient. This gradient of the line is much more shallow than the dashed line, and so you know that they have to move towards. So very close by here, the cobweb diagrams, I'll just do one arrow like that, should move towards, and you see that it moves away from this fixed point. So moves away from this fixed point, move towards that fixed point. Okay? And that's basically all the observations. I can write a little arrow here. This tends towards 0. So that's stable here. And this here is unstable. Okay. Now notice that when mu, remember when we did the analysis before and I said, oh, I'm not going to talk about when mu is very negative, because we're only interested in the behavior near or equal to 0, but you could do that yourself, right? You make more of these plots when mu gets to be very large and negative, right? Very large and negative. And what's going to happen, you see, is that this point here, which is previously so I think what happens is that it's a good question of what happens when mu is very large and negative. Okay, I see what happens. If mu is very large and negatives, then this behavior is dominated by mu times x. I know this because mu will be bigger than 1 in magnitude, and I know that x squared near the origin is going to be dominated by this, I think. I think it's a guess. So I think what's going to happen is that this graph here will get increasingly steep, and then it's going to come down and then intersect this line here like a gradient of mu times x when mu is very negative. That's my guess, you see. So, and then this, yeah, that's right. And then this gradient here, which was previously safe, it was previously stable, is eventually going to develop a gradient of -1, and then it's going to go unstable. That's basically what happens when mu is less than 0. That's my guess without a computer. Okay, so then what happens if mu is greater than 1? Well, when mu is greater than 1, you see, when mu is equal to 0, when mu is greater than 0, here's your graph. So when mu is equal to 0, the fixed point which was on the left here then starts to move towards the origin, because this fixed point is always at mu. It moves towards the origin, and at that point there, you have a sort of a double root. You see, you have a double root there. And to do that analysis, you don't know anything about that analysis. You'd have to basically go and study that problem, the very special problem of mu equal to 0. You have to study that problem in isolation, which you can do. You just study x minus x squared. But the point is that this root here moves towards the origin when mu is equal to 0. When mu is greater than 0, it starts to move onto the top side. And so the root at 0 remains. You still have that root at 0, and then it comes down like this, you see? Okay. Now, firstly, when it first crosses, it's not a very good picture. When it first crosses, this here, I'll still call it x minus, and I'll call this one x plus, just so I can keep the same naming convention as before. When it first crosses, when this root here first crosses the origin, this gradient will be very shallow, right, when that happens. And so this will be a stable fixed point, whereas this one here will be an unstable fixed point. So the origin, which was previously stable, is now unstable, and the other fixed point, which the one that's not at the origin, the one at x equal to mu, is now stable. So this is a stable fixed point, because you can see the gradient is shallow compared to the line. It'll be moving towards this point, whereas it'll be moving away from the origin. So this is unstable. Okay? And so the stability changes. And you draw then, so now that you've understood how it works, you understand the bifurcation diagram. And by the way, this issue I said of mu being, the stability also changing when mu becomes very large, you also saw it in the picture that I just erased, which is that when mu gets bigger and bigger, that intersection, that secondary intersection here, will then eventually become extremely steep, exceeding a magnitude of exceeding a magnitude of 1 in the gradient, and then the stability changes. But you're only interested for now of the behavior near the origin. Okay? That's the difference between a global analysis and a local analysis. Okay, so now that you've completed the problem, you've done the fixed points, you've done the stability, you've done the cobweb diagrams, you have an understanding of what the fixed points are, you now draw the bifurcation diagram, right? So you basically draw this diagram here. Now, this is now mu, and now this is x. And we drew it before for the generic problem. We drew it for the problem where we don't know the coefficients, these coefficients b0, b1, b2, right? We draw it here for the precise coefficients, and for the precise coefficients, we know that x equal to 0 is always a fixed point of the system. We know it always exists, so it should be everywhere spanning this line. And you know that firstly, it is stable on the left when mu is less than 0, and it goes unstable on the right. So that's what you do with this picture. When you do it yourself on a homework, make sure that it's clear that you're actually drawing on the axis. You can do it in a different color if you like. So x equal to 0 is stable here, and then the stability changes as I cross the origin. On the other hand, I know that when mu is less than 0, the fixed point is negative. It's when x is equal to mu, right? So it's on this region here, and I know it's unstable on that side there. And then I know the stability changes on the right-hand side. And this is the line x equal to mu. Okay? And then you label this TC, if you like. Transcritical. So make sure you label your bifurcation diagram. This is how you make a bifurcation diagram. Solid for stable, dash for unstable. Label your bifurcation points. Okay? Good. Right. Now let's go on. So we've done the transcritical case, and you understand now the basic philosophy. You're basically going to get more and more specialized situations with further restrictions on these coefficients. The transcritical bifurcation required that this A1 was equal to 0, right? Now what we can require is that one of the key coefficients for the transcritical bifurcation was also equal to 0. So this is an unnamed case. If you go to the lecture notes, it's unnamed. Let's just call it case star here, because it's not actually going to lead to a situation, but let's just do that, that analysis. So you take this thing here, and the next specialized situations is, let's consider B0, well, A1 is equal to 0. Sorry, B0 is equal to 0, but A1 is not equal to 0. So A1 is not equal to 0, and B0 is equal to 0. If B0 was not equal to 0, then you have a saddle node bifurcation. You have the possibility of 1 and 2. Let's say, okay, let's say that the requirement that you had required for the saddle node bifurcation is now invalidated because this 2 is not equal to 0. And the question is, what are the possibilities? So there's a few possibilities to go through, but the most obvious one, because you don't really know what to do, you just try the obvious one, which is I'm going to balance 1 and 3 together, because 2 is not going to exist. So I'm going to balance 1 and 3, and I'm going to try to see, is that much greater than 4, 5, and 6, and so forth and so on. If I balance 1 and 3 together, then I have B1 x times mu is like minus A1 times mu. Okay? And that tells me that x tilde minus A1 over B1. But the problem is that this quantity here, minus A1 over B1, is just a number, right? It's not a number that tends to 0. And throughout this analysis, you've assumed that the fixed point, when you do this analysis, the fixed point is always near 0. That's the fundamental assumption behind all this work. So this is not a legitimate balance when you do the local analysis. So this is not a legitimate balance. Not a legitimate In this local analysis, from the get-go, 2 lectures ago, we started off with the assumption that the fixed point when mu is equal to 0, the fixed point is located at x equal to 0. And you're looking at the behavior of this fixed point as it splits or as it changes stability when mu increases past 0, goes from the negatives to the positives. This balance doesn't work because this balance essentially gives you a fixed point which is away from 0. So essentially this case does not yield any fixed points. So the next thing, no fixed points near x equal to 0 for the case of mu is equal to 0. Okay, so then the next thing to do is you can, by the way, you can go through even more possibilities and to assure yourself that it wasn't just the case of doing this particular dominant balance. The very last bifurcation of this chapter to look at is the Pitchfork Bifurcation. And in the Pitchfork Bifurcation, you're going to assume that one of the quantities which was involved in the transcritical bifurcation, 2, 3, and 4, is not going to be there, and you need to bring in the 5 balance. That's basically the name of the game. You keep on going deeper and deeper into the series, getting more and more conditions. And by the way, the deeper you go in the series, the more restrictive that condition is. So in many ways, you're most likely to see a saddle node bifurcation. You're most likely to see a transcritical bifurcation. The deeper you go, the more restrictions you have to place on the coefficients, which means that it's a much more restrictive function f that has to be designed in order to produce this phenomenon. So we had case A1, which was the saddle node. We had case A2, which is transcritical. We had a case that yielded a contradiction, and so it was not involved at all. And then finally, we have case A3, which will lead to the Pitchfork Bifurcation. Okay? So the case A3, let's assume A1 is equal to 0. So this was the first depth that you needed to get a transcritical bifurcation. The other key quantity that you needed to be not equal to 0 for the transcritical bifurcation was this B0. Because if this B0 was equal to 0 in the transcritical bifurcation, you would no longer have the quadratic formula. You would no longer have 2 roots, and then all the analysis that you would have done, you would see that it doesn't work anymore. So the next assumption in this hierarchy is B0 is equal to 0. Okay? And then now you need to solve the equation 3, 4, 5, 6, 7, and so forth and so on. So now you need to approximate 0 is equal to, I've got my B1s, those are still there. So for instance, some of these dotted terms, this will be order x squared times mu. Order mu cubed, right? We're not going to write that out. But we have to verify to some degree of certainty that they're not going to come back and bite us in the bum, and they're not going to be involved in this analysis. Okay? Right, so now the most obvious balance to try is just 1 and 2. You say, well, why do I need 3 at all? 3 looks pretty far away. Let's just try 1 and 2. And that's what you should. Oh, I realized the issue. The issue is I relabeled my numbers. So this is a 3, 4, and 5. I'm going to call this 3, 4, and 5 so that we can be consistent. Okay. By the way, this is the first case. This is the first case where I think in one of the discussion board questions, it was asked, well, why do this whole dominant balance business in the first place, right? This was back when you were doing the series question, the series approximations. I was asking you to approximate roots of a quadratic, roots of a cubic, and in your problem set, roots of a quartic. And someone had asked, well, why bother going through this procedure? Why not just substitute in the series and then try to solve for each of those terms in the approximation? And the answer to that question is that you can do that, no problem. but the problem is knowing what series to put in the first place, right? Should they go up in what powers of mu, of x? How should they be scaled? And that's what the dominant balance gives you. It gives you a kind of a back of the envelope way of estimating what is the right balance to go with. And this is the first time, this example, the pitchfork bifurcation, that's the first time in which it's not obvious what the right balance is, for reasons that you'll see in a second. Now, again, the most basic assumption, if you don't know how to do these balances, right, that's the thing, you can't be afraid of trying. You just try different things, and you just see, do I get a contradiction? If you don't get a contradiction, then it's a legitimate balance, right? And you just try from left to right. So the most basic attempt will be 3 and 4. Okay, so let's just try. So you try 3, 4, 3 balancing 4, and let's assume that that's much larger than 5, 6, and so on. And again, you just try it and you see where it goes. So here I'll have a b1 times x times mu. Balancing, I move the other one to the other side, I have a minus b2 times mu. Okay, and then mu squared, sorry, I was confused there. b1 x mu balancing minus b2 mu squared, and so x is then minus b2 over b1 times mu. So the first thing to notice is that this always exists, right? For mu negative and for mu positive. This is the way that you always do the analysis. You find your fixed points, then you make a comment about their region of existence looking at the formula. This always exists when mu is less than 0 and when mu is greater than 0. And it's a line. So it tells you that there's always a fixed point, right, which follows the equation of a line in the x mu plane. And it's there on the left and it's there on the right. But the problem is that this is not the only possible balance, 3, 4. Actually, before we go, I'm sort of jumping around here. Before we go, let's make sure that 5 is smaller. Let's make sure that this is a consistent balance, right? So let's just check. So 5 is then order x cubed. And if x is order mu, then this is order mu cubed. And the question is mu cubed smaller than the things that we were using, 3 and 4? This is indeed smaller than 4, which was in balance with 3. So this is a consistent balance. And then you can try for 6 as well, and so forth and so on, and make sure that if you did try this, so for example, x squared times mu, if x is order mu, this is mu cubed is smaller than mu squared, which was 4, right, when mu is small. Okay? Good. So this is a legitimate, consistent balance, but the key is that it's not the only balance. Just like when you studied the cubic equation with me and the quartic equation, this is not the only balance. What other balances might work? Well, you see, it's this mysterious term 5. It's this mysterious term 5. So again, you're going to try 3 balancing with 5. Okay. Now, is it obvious you shouldn't do 4 balancing with 5? No, it's not obvious to me right now. It's not obvious. I mean, I had a look at the notes. The notes told me it's the 3 balancing 5, but we can also ask her, well, why did you think of 3 balancing 5? Why not try 4 balancing 5? Let's try that a little bit later. And hopefully you get a contradiction. So let's try 3 balancing 5. And we're going to assume that's much greater than 4, 6, and so forth and so on. 6 is just all the other stuff that we've ignored. Okay. So if 3 balances 5, then b1, then I have c naught times x cubed balancing minus b1 times x times mu. Okay. I ignore the x equal to 0, 1, because you always want an x which scales with mu. That's the point of this analysis. So, and you're left with c naught times x squared is balancing minus b1 times mu, so x is like plus or minus the square root of minus b1 over c naught times mu. And let's do that. We're going to write the mu like that. So you see it's the root mu. And the question is this a legitimate balance? So we have to put this answer here into 4 and 6 and so forth and make sure that they are indeed smaller than 3 and 5. So you check. So 4, for instance, 4 was order mu squared. Scale is like a mu squared, right? And is mu squared much smaller than x times mu, right? So or let's take 5. 5 is equal to order x cubed, which is order, that's mu to the 3 halves, or a power of 1.5, and the smaller power is the bigger one if the thing that's being taken to the power of is small. So this is much larger than order mu squared, right? The bigger powers are always smaller when you're near 0. And so that's a consistent balance. Now, you have to check 6 and so forth, and so forth and so on, and make sure. Okay. This is the difference between applied mathematics and pure mathematics, right? So the method of dominant balance is not a rigorous method necessarily. You don't think of it as a rigorous method, right? In theory, you would have to try this. You have to do this, to higher orders and to make sure and to do things properly. But for us, it's just the first attempt just to check this consistency, and it gives you a legitimate approximation. I should say that in practice, in research, right, in research, you're often not too bothered by necessarily the question of rigor. You're using this to get you that first intuition of what the solution is supposed to do. Then you go to your computer and you check with graphs. Then you check with your numerics, and that gives you the evidence to believe that this is the right balance to use. Afterwards, once you have the intuition, the evidence, then you can begin to solidify that framework and do things in a rigorous way. This is often how you do research. Okay, so this is a consistent balance, and I would rather not hold you on any further than, I know we started a bit late, but I'm not going to hold you on any further because I'll see you on Friday. Right, so let me just summarize the key things to know in today's lecture. We finished up with the transcritical bifurcation. The transcritical bifurcation is a bifurcation where it goes from 2 fixed points to 2 fixed points. Now what we're about to see, on Friday, what we're about to see is that in the pitchfork bifurcation, you always have, remember we found one approximation which was x is like mu. X is a constant times mu. This always exists either side of mu. Mu less than 0, mu greater than 0. Okay? And then the approximation that we just found was like a square root of mu, right? And so the square root of mu is only going to exist on one side of mu. It's going to be whatever side it's a real number, right? So you go from one fixed point on one side to 3. 1 plus the 2 square roots, right? Or you go from 3 to 1, depending on how it works out. This, when you draw the bifurcation diagram, will eventually look like a pitchfork. That's why it's called a pitchfork bifurcation. You go from one fixed point, which always exists on either side and looks like a line, to 2 that look like square root branches. And so the next step for us in Friday's lecture is basically do the cobweb diagrams for this, figure out what the stability is, and that's going to put an end, hopefully, to Chapter 5. All right, any questions before we disband? Oh, sorry, someone asked to move the camera, and it's really hard for me to see the chat at the moment just because of the way the camera works. I'm going to have to see whether I can fix my computer by Friday. Or I'll figure out this setup. But all right, any other questions before you all disband? Thank you very much. I hope my computer gets better as well. Otherwise, I'll be taking donations for a new computer. Or we should play some ads, or I should do some product placement. Thank you very much. Okay, see you all on Friday. Have a good rest of the day.